Welcome students. In today's class, we'll look at training process for multi-layer perceptron or neural network. Training process of the multi-layer perceptron involves two phases. One is the forward propagation and the other is the backward propagation. In the forward propagation, we are going to predict the output for training set samples. And in the backward propagation, we are going to calculate the error, that is the difference between the predicted output and the training set output. And then we are going to adjust the errors to reduce the error. That is, second phase is about calculating the error, and then error is being calculated by finding the difference between the predicted output and the actual output. And then by in the back propagation, the other one is, that is, we are going to we update the weights or adjust the weights so that the aim is to reduce the error. Now, when we have to reduce the error, we are going to use the algorithm called backpropagation algorithm. That is, backpropagation algorithm aim is to minimize the error. That is, minimize the error so that the updated weights are going to used next, so that we will pass through this forward propagation and back propagation. That is, this loop will continue until we are going to get the weights which are going to reduce the errors. Now, starting with the back propagation algorithm, let us consider an output neuron J, that is the neuron J at the nth iteration. Then the error signal is defined as, that is the difference between the desired output, that is dj of n minus yj of n at the jth neuron. Instantaneous error energy for the neuron J is given by E of n equal to 1 by 2 E square J of n. Let us represent this by the equation A. The total energy we get by summing 1 by 2 E square J of n over all neurons in the output layer. Therefore, E of n equal to 1 by 2 summation J is for all the nodes in the output layer. That is, if we have two nodes in the output layer, then C is going to take the value 2. If there are 3 nodes in the output layer, then C is going to take the value 3. That is, it runs from 1 to 3. Therefore, E of n equal to 1 by 2 and summation of all the errors, that is Ej of n, that is, which includes all the nodes in the output layer. Now, average square error energy is being given by, that is E average equal to 1 by n, and n is number of patterns contained in the training set. That is, if we have total number of training examples in our set as n, then n is the number of patterns at the training example. That is, if we have features are x1, x2 up to xn, then how many rows of instances are there? This will be with respect to the n. That is, how many rows are there. And E of n and E average is the function of all parameters of the network. That is, this includes weights and also biases. For a given training set, E average, that is EAV, is the cost function. Objective of the algorithm is to minimize the total overall average error. Now, for training, we'll consider the simple method of training, that is weights updation. Weight updation is by pattern. That is, as I said, that is, we will take this first training example and then do the forward propagation, and then we do a backward propagation, and then we will update the weights. After the first training example, we'll do this completes one epoch, and then we go with the second training example and do the forward propagation and the backward propagation. That method we will follow. Now when we have to learn how to update the errors. That is, adjustment of the weights is errors are computed for each pattern. That is each training example. We'll consider the neural network structure as shown here. That is, if we take the neuron J, its output is given by Ej of n, that is the error of the output node J at the nth iteration. Desired output is dj of n. Here -1 indicates that as subtraction, because when we have to compute the error, we are going to do the subtraction between the predicted output and then the desired output. And here yj of n is the predicted output. Pi of pi is the activation function, and then Vj is the summation which is being induced by multiplying the inputs yi's here in this case with the weights, that is wj's. Now Vj, which is here in this one, is we are going to get by summing from I equal to 0 to m. That is, we are the input is running from 0 to m, and in y0 equal to +1 is the bias term. Therefore the input is held at constant +1, but weight is given by wj0 of n equal to bj of n, which is going to indicate for the bias. Similarly, if yi is the input and the weights are given by the wj of n, here the arrow marks indicates because this goes to the this input also goes to the other neurons. Therefore, this indication is being given because there will, after the neuron J, that is, there will be other neurons also here actually. Therefore, the connections will go there. And now yi is the layer which is the previous to the output neuron. That is, if we had the input layer, and then we have the hidden layer, and nodes will be here, and then output layer, and we will be having the nodes. That is, this J neuron will be getting connected from the layers from the previous this thing. And similarly, if we have one more hidden layer, then here this will get connected. And from the input, this hidden layer will be connected. Therefore, the actual output yj of n is pi j of vj. Because in the diagram you can see here, we have here yj, which is coming from the activation function. For the activation function, the input is vj of n. That is similar to the LMS algorithm. The backpropagation algorithm applies the correction to the synoptic weights wj of I of n. That is, now when we are here, when we are concentrating on here, our concentration is on like how to correct this error. What is the updated error? Sorry, updated weight, what we have to do. That is, we have to find out what is the updation value we have to add to the wj of n. Now, this updated weight will represent it as delta wj of n. That is, what is the updation value we should find. That is, for the old weight value, that is, if I have wj is my old weight value, what is the updated wji of n we should add, so that we will get wj new act. That is, wji new equal to old with updated weight. That is, this delta wji of n is proportional to the partial derivative differentiation of e of n by differentiation of wj of n. That is the error what we have. And now this dou e of n divided by dou wji of n is can be given by a chain rule. That is, you can observe here, this is our total error. That is, this ej of n will be given with respect to the yj. Therefore, here we have, that is, this total, that is ej, e of n with ej, and then ej of n with yj, and then yj is with respect to activation that is sorry, the activation for the activation function, the input is Vj. Therefore, Yj will be coming from the Vj. Therefore, Yj differentiation of Yj of In with Vj of n, and then Vj of n with Wj of I. That is, look at the diagram and then look at how we are doing it. That is, differentiation of E of n is with respect to differentiation with respect to the small ej of n, and then this ej of n is coming from the yj of n, and then this yi yj of n is coming from Vj of n, and then this Vj is of n is from Wji of n. Therefore, this term is being expanded using the chain rule. Now we'll look at how to find the differentiation for all these individual terms. Now, taking the first term in this expression, that is dou E of n by dou Ej of n is equal to Ej of n, because we had here this term, that is from the equation A, E of n equal to 1 by 2 Ej of n. When we differentiate, this 2 will get cancelled. Therefore, for this differentiation, the term remains as Ej of n. Now differentiating the equation 1 we had Ej of n equal to Dj of n minus J of n, and differentiating on both the sides with Yj of n, we will get, that is dou Ej of n divided by dou Yj of n as minus 1, because this Dj of n is a constant. Actually, it will not vary with respect to Yj. Therefore, this will give us the term minus 1. Now differentiating the equation 5. Equation 5 we had, that is yj of n equal to pi j of vj of n. Therefore, when we differentiate that one with respect to the vj of n, we will get the pi dash, that is differentiation term with vj of n. Now, this is our main equation which we had. Now, to get dou E of n by dou Ej of n, differentiating the, sorry, we are not here. Sorry, we will come back here. We got all the terms, that is up to here, we got, that is we got here. Now, finally differentiating the equation 4, that is equation 4 we had this one, Vj of n is the summation I equal to 0 to m Wji of n and Yj of n. So Yi actually, because the input is from here, that is Yi of n. Therefore here it is Yi, because this previous will be for the input which is coming from the ith neuron, actually previous. Therefore it is Yi of n here from this side, and this side it is J neuron. And now Vj of n is, that is summation what we got here. And now we were here, this differentiating this particular term, that is this equation with respect to the Wji of n, we are going to get with the term, that is Yi of n. And now the whole term, that is dou E of n by dou Wj of n is minus Ej of n, because this is minus from here. We are substituting in this main equation. This is our minus 1, and this differentiation term is Ej of n here. And now this Yj of n by Vj of n, we got pi dash j of Vj of n, and then Vj of differentiation of dou Vj of n by dou Wji of n is given by Yi of n. Therefore, now when we substitute all these terms, our equation, that is this final term, that is differentiation of the error E of n with uh, differentiation with wji of n is minus ej of n and then pi dash j and vj of n and yi of n. Therefore, corrected error, that is delta wji of n, sorry, this is not the corrected error, the updated weight, what we have to get, applied to wj of n is defined by the learning rate, that is eta, and then differentiation, that is dou e of n by dou wj of n. That is n is the learning rate parameter, and why negative symbol, because the direction negative to go with the direction to the direction of the gradient, because we have to go with the opposite this thing. Therefore -1 is for the direction negative to the direction of the gradient. Therefore, our updated weight, what we have updated delta weight, what we have to apply to the old weight is given by minus of eta learning rate multiplied by dou e of n by dou wj of n. Now, we will take this one, that is we had from the previous until now the derivations, we had this one, and then this delta wj of n is was this term, and then just recollecting, that is we had differentiation of e of n by differentiation of ej of n was ej, and differentiation of dj of n with yj of n was -1, and differentiation of yj of n by vj of n was pi dash j of vj of n. These are the terms what we have. We'll just keep. Now, when we substitute, that is our delta j, what it tells, minus of eta and then differentiation of e of n with wj of n. Now, when we take this term and then when we multiply with this particular term, the negative term goes off and then the learning rate will remain, and this terms what we had, we are going to get this term. Therefore, now we will call this entire term ej of n, pi dash of j and vj of n as delta. That is, this is small delta. We sometimes we call this as this also a delta, but this is uppercase delta, and this also a smaller case delta. Delta of j of n is y of n. That is, delta j of n is the local gradient which is defined by, that is how it comes, this delta j of n is from minus differentiation of e of n with differentiation of vj of n. Because you observe this one, because we said this delta, this term is delta j of n, but how it is coming from? Because this term is what? Ej of n, and this is -1, and this was pi j dash of vj of n. Now this term, that is when we take this negative and this negative will cancel out, but this is coming from this particular term. Therefore, that is this equation, we call it as 6, because pi dash of vj of n is a derivative associated with the activation function, and we call this pi dash j of pi dash j of vj of n as a local gradient for the output neuron j is equal to the product of the corresponding error signal, because this is our error signal for that neuron, and the derivative, that is uh, pi dash j of n associated with the activation function. Updated weight, that is delta updated weight, updation, what we have to do, wji of n is learning rate eta with delta j of n with yi is our known input signal, and the learning rate will be given. That is, when we are given with input signal and the learning rate, now when we have to update the weight, we should compute this delta j of n. Therefore, should know how to compute this local gradient delta J of n. Now, if the neuron J is output node, then how we are going to compute? That is, that will be computed with delta J of n, Ej of n, and pi dash J of Vj of n. Because we have computed this derivation, this delta J of n, considering and the output node as the J as an output node neuron. Therefore, if neuron J is output node, this is the expression for the delta J of n. Now, the other case what we have to consider is if the neuron J is the hidden neuron belonging to the hidden layer. That is, as I said, in multi-layer perceptron, we have the input layer and then hidden layer and then output layer. Now, we will be having some nodes here, and then we will be having the nodes in the input, and similarly we will be having the nodes in the output. All this will be connected. Now, until now in the derivation, we looked at how to compute the updated weight for the neuron J in the output layer. But if the neuron is the hidden neuron, that is which is there in the hidden layer, then how to compute that updated weight, what we have to see. Therefore, we'll consider this diagram which is shown here, that is considering the neuron K as the node in the output layer and the neuron J in the hidden layer, then how to proceed. Now, you can observe here for the if neuron K is the output neuron, the input will be coming from the previous this thing, which is from the neuron J. Output of the neuron J will act as an input to the neuron K. And similarly, this side, if I have another neuron, it will be there because if it is a hidden, at least the input will be there. That acts as an input for this neuron node. Now, we will compute this delta J of n. That is what I said. That is when we have to update the weight, eta is given and then input is given. Only there we should know this delta J. If that is delta J of n. If it is an output node, we can compute that one using this formula which is shown. But now we are looking at the question if this node is for the hidden node and how to compute. Therefore, we will now learn how to do this one. Now, this delta J of n can be given by minus of dou E of n and dou Vj of n. Because here I said this eta, 1 minute, that is here we have seen that is delta J of n is given by minus dou E of n with dou Vj of n. How we got this one if the node was an output node. Similarly, it becomes for the hidden node also. Therefore, we have considered this one. And now this one we can expand, that is E of n with yi of n and yi of with respect to the Vj, because that is what we should get, because we will be getting this y from the Vj, therefore the chain rule. And now we know this differentiation of yj of n with vj of n is pi dash of vj of n, because it's a differentiation of this term which already we got previously also. And now this e of n in the sense it's a total squared error for all the nodes. Therefore, it becomes 1 by 2 and then summation k belonging to the C and ek square of n. And now we will differentiate this with respect to yj of n. Therefore, it becomes summation of running through k, because if there are k nodes, that is C here is the set of output neurons. Therefore, k will run through all that one, because this hidden node is connecting to the output node. And now here we will get a differentiation of ek of n with yj of n, because the 2 will get cancelled, but this differentiation will remain and it will be the summation of all the nodes. Now proceeding further, we had this term here. Now this term you can observe, that is E of n by yj of n, will be given by the summation of Ek and summation of the error Ek with differentiation of dou Ek of n and yj of n, because we are here, and then it will be coming from all the nodes here, therefore the summation goes through. And now when we take this one, now when we have to expand this term, differentiation of Ek of n with differentiation with yj of n, we have to take with respect to this Vj of n actually. Therefore, here this term further gets expanded as dou Ek of n by dou Vk of n, and then dou multiplied by dou Vk of n by yj of n, which is coming from that this thing. Sorry, 1 minute. I think not this one here. Ek with Ek with Yk here, and then Yk with Vk here. That's the this is the thing. Therefore, we got this expansion further. And now we Ek of n is dk of n with subtraction with Yk of n, and Yk of n we can get by the activation function with Vk of n. And now when we differentiate this one with respect to, that is this 10th equation with respect to the Vk, we'll get minus of pi dash of k of Vk of n. And now for the neuron k, that is this neuron k, when we take this Vk of n is a summation coming from all this terms. This is summation coming from all these terms. Therefore, j is equal to 0 to m, and then wk j of n and yj of n, which becomes, that is m is the total number of inputs applied to the neuron k, that is which is coming from all these terms. And now rewriting this equation 9, that is this one, when we take back actually, take this one, that is this becomes negative, because here we got this negative symbol here, and then Ek of n will remain, and then this term, that is here, uh, this term value we will substitute here, and then similarly this term value we got as wkj of n, that we will substitute. That is finally differentiation of E of n with yj of n is minus summation running through k, ek of n, and then pi dash k of vk of n, and then wkj of n. Now, rewriting the equation 9, that is what we got seen here. That one, we had this term, but now we will write it in terms of this delta, this thing. That is, we will consider now this as our delta term, that is delta k of n. That is delta k of n. This way we will write this term, because from this, sorry, 1 minute, this now ej and minus ek, yeah, same way from the equation 6, because equation 6 was this one only, we can stay here, that is equation 6 was this one, which was ej of n, and then pi dash of j of vj of n, because we got it from here, we can see once again, which was here, this equation 6. And now we are here. Now substituting the equation 14 in equation 7. Equation 7 was this equation, delta j of n and minus differentiation of k of n with yj of n, and then pi dash of vj of n. Now when we substitute substituting the equation 14 in equation 7, we are going to get finally, that is 7 was this term, and 14 here is what we can see. This is our equation 7, and this was our equation 14. And now this value we should substitute here in this one. Now when we substitute, this negative symbol goes off, and then we will be left with this pi dash of j, because that is what we are going to have, and wkj of n, and then we'll represent this term, substituting the equation 14 in for 14 we have to substitute in the equation 7. Therefore here this negative term goes off, and then this delta k of n and wkj of n will come here, and then in this term we had pi dash vj of n that will remain. The summation and the negative symbol will go off. That is now what is observation from this term. That is, this is for the case where we are considering the node j is the node which is there in the hidden layer. We are expressing now this particular local gradient delta j of n as a gradient of hidden layer neuron j in terms of local gradient of the output layer neurons, because this delta k was our output neuron, delta j was hidden, because in the diagram you can observe this was our neuron k and this was our neuron j, which was the hidden node neuron. That is, what is the summary we have to take is, we are expressing the local gradient of the hidden layer neuron j in terms of the local gradient of the output layer neurons. And now summarizing finally, that is what is our update rule is, that is updated or the corrected weight wj of n is defined by the learning rate eta with the local gradient delta j of n with the input signal of the neuron j, that is yi. Because for the if the output node j is the output node, we got delta j of n as ej of n and pi dash j of vj of n. If it was a hidden node, we got this term, that is delta j of n as pi dash j of vj of n and summation. That is what we had here, this derivation what we did here. That is, now if it is delta j is the hidden, this is our expression. That is, a local gradient delta j depends on whether the node is the output node or the hidden node. That is when we have to do the updation of the correction. Now to compute the delta j of n, we have to consider two cases, whether the node is the output node or the hidden node actually. And depending on that, we are going to do the calculation. Thank you.